Okay, so I don't think it's going to take very long. I purposely made a shorter lecture because I know we'd be going over the test. And I actually did record the discussion on the test in case people are interested. I'll upload that to YouTube like I normally do. But we'll now talk about some different analyses that are raster-based, and we'll talk about different ways of modeling elevation, and then we'll set you free for spring break after that. I'll keep an eye on the clock. It's 8 o'clock already, but I think we'll be done by 9, no problems. The first topic tonight is resolution. And what do I mean by resolution? Resolution is a term where we talk about measuring the accuracy of a raster. Now, though I've genericized that with raster, very often this is specifically in relation to remote sensed raster data. So how would we measure the accuracy of remote sensed raster data? Well, there's 4 different ways. And accuracy, maybe there's a better way to put it. Measuring the accuracy and measuring what is being, the breadth or scope of what is being measured. And there's 4 different resolutions that I'm going to talk about now in remote sensing raster data. The first one, spectral resolution. The spectral resolution of a remote sense raster data set measures the wavelengths that are being measured. And we looked at the electromagnetic spectrum last week and all the different wavelengths. We looked at the rainbow, both the visible color, radio stations, and all that. So for example, here's 4 different views of New Jersey at different spectra. It's too bad that's not a color slide. It just shows that in this particular case, the spectral resolution of this image is green versus red, near infrared. I think I should just say IR for infrared. I showed a slide like this last week too, I think, if I recall. Yeah, might be the very same one. We're reviewing. So the spectral resolution of an image might be wide. I mean, you could remote sense an area in all of these wavelengths or just one. So when we talk about what wavelengths are being remote sensed, that's referred to as the spectral resolution of the image. So if someone asks, what's the spectral resolution of your image, you might get an answer like infrared, ultraviolet, etc. Make sense? Temporal resolution, you could probably figure out from the name. How often is the imagery taken? Imagery often is taken, I mean, you can have a one-off image, it's a custom request, but there are images that are taken at regular intervals, and that's the temporal resolution. You might have a yearly shot. Often when we're looking at in a broad scope environmental review of an area, you're looking at the vegetation this year versus last year, or this year versus 10 years ago. Remember this I did show last week, the Mount St. Helens image from 1983 to 2000 something. The temporal resolution was 20 years because you're looking at the change over 20 years time. And we saw in that slide how much Mount St. Helens is revegetated since the 1980 eruption. Temporal resolution may be a lot less than 20 years though. For once, there is some. We don't have to worry about precip here. The temporal resolution of this remote sense data is 5 minutes. Looking at this weather radar map. So we can use the temporal resolution. Temporal resolution is important when you are interested in change detection, or what is changing over time. And that can, as I said, that can be a wide range of things. It can be what changed over 20 years at Mount St. Helens, or what changed in the last 5 minutes, such as this radar map. So you can see where I'm getting the temporal resolution there. You can see in intervals, where the rain has been from 7 o'clock till 8 o'clock a few minutes ago. I didn't know there was any rain around seems pretty clear on it. Looks like it's going to our south, which is good. So this is a real live current example of a temporal, where temporal resolution would come into play. Radiometric resolution is the third type of resolution we'll discuss. And I do usually have a question and name the 4 resolutions or name 3 of the 4 or something like that, just as a heads up. The radiometric resolution measurement is the sensitivity of the detector to differences in signal strength. So how well we can sort of measure, oh, they don't have a scale on. Go to the National Weather Service radar instead. So how well can the remote sensing equipment detect changes in intensity? And if I remember right, it does show in the Doppler weather radar map here. Over here on the right, we have this legend that indicates the intensity of the precipitation. And I don't, my brother's a meteorologist, he could tell me, it has to do with the reflectivity. So the more that's reflected back, we talked about that last week, the more that's reflected back, the denser the rain is. If you visualize that as more, if the rain is heavier, it's covering the Earth's surface more. More of the atmosphere is filled with raindrops. So more of the radar signal will be bounced back. So I think that's why it says decibels here. I think that's the decibel signal of the radar that's returned. I'm not 100% sure on that. So here, but this is an example. The radiometric resolution here is in units of 5. I can tell that, there's some, in the Genesee Valley here, there's some heavier rain around Dansville right now. So that is a dBz value of 20. There's also some pockets of heavy rain in Pennsylvania and New Kenyon. That's in the range of 15. I can't get any finer with this map. We can see where it's in the range of 15 and 20, but you see what I'm saying? I can't tell you whether it's 17 or 18. You see where I'm coming from? The radiometric resolution is not fine enough. In other words, the detail being returned, they might have better details, they're just generalizing it for the public. But the detail as far as intensity of rain on this map only goes down to the unit of 5. So the radiometric resolution will be 5. And again, it's detecting differences in signal. Does that make sense? And in a more genericized version, I think the radar was a good example, but another could be detecting differences in color. An 8-bit radiometric sensor can detect 256 different colors. So this is an image with 256 different colors in black and white. A 4-bit image only shows 16 different colors, and you can see how it's grainier. And in the 1-bit example, this radiometric image can only detect 1 color, or 2 colors, black and white, yes?
That's supposed to say radiant levels, right? Not radiant rebels? Okay.
Yes, radiant levels, rebels. Yeah, thank you. I've never. I'll ask him, what's a revel? I don't know the answer. That's right, we're reveling in spring. I'm not going to be able to find this in. Oh, it has Photoshop. good shot. I've never used CSS. This might with threshold, I've converted the owl picture to 1-bit radiometric resolution, black or white. Versus now, the resolution is, I didn't take this image, I don't know there's 8 bits. In an 8-bit image, that allows, remember, 256 different colors. So you can render this nice picture of the owl quite nicely with 256 possible colors. But if I take this down to 1 using the threshold tool, now it's 1 bit. So when the less bits, the radiometric resolution has been decreased, reducing the number of possible values from 256 to 2. And with 2, I can only use, the only 2 values I see are black and white. Hopefully that helps illustrate also radiometric resolution. So we looked at the example of the radar and a snowy owl. Yes?
When we're remembering the name, are we remembering the levels?
I'm not worried about the levels. Yeah, but I would focus more on the name and the concept. I won't ask, for example, how many levels are with 4-bit. If that's what you're asking, I'm not going to ask something like that.
Is this like the radiometric resolution, just like when you use the, when you scan the paper and they ask you how much
Exactly. Yeah, how many colors? Yeah. Not the dots per inch. When you scan a paper, it asks dot per inch. That's the next slide. Radiometric resolution, one of the things it asks is how many colors, or black and white. Black and white would be 1 bit, like the owl I just showed. Does that help explain?
Yeah.
What the other thing you talk about actually would be on the next slide. Does everyone understand this? It's the difference in values. I'm not getting younger. My radiometric resolution, my eyesight's going down. I can't see. As I'm looking at your names, I'm holding the papers like this. I used to have good vision. It's gone. So detecting the different colors is difficult even in your eyes as you age. I don't even notice colors like I used to, I don't think. Dr. Markman, when I took this class in 1993, the study has shown that for some reason, women on average, obviously every individual is different, notice 5 times as many color as the average woman notices 5 times as many different colors as the average male. I don't know why, but I think that was an interesting point. When it comes to color radiometric resolution, I think that's an interesting tidbit that I remember when I was sitting here that is worth noting. Any questions? I think we have radiometric resolution down. The fourth and final resolution is something you would also set on when you scan your paper. Spatial resolution is the smallest distance that can be detected. It has to do with the pixel resolution like we talked about before the first exam. So in this case, more generalized, spatial resolution is the smallest object that can be discerned on the image. Yes?
I saw the unit, I remember it's not wrong, it's RPI or something?
DPI on the scanner, dots per inch. So even though that's not spatial in terms of world mapping, but it is the same thing. The higher, if you're scanning out like an old family photo, the higher dots per inch, the more smaller things you'll pick out in the photo.
Larger files.
Larger files, yeah, that's the downside. And it's exponential. If If you have 2 dots per inch, like that makes 4 squares. If we go to 4 dots per inch, now we have 16 squares. So when you increase the dots per inch, the file size increases exponentially.
Where's dots?
Okay, so each square is a dot.
Okay.
They really shouldn't call it dots per inch. They should call it pixels per inch or something like that, because they're not dots. They're little cells. But DPI is what they call them. So the X's would be the dots. So in this space, if you scan this paper and you said 2 dots per inch, you would get 4 dots, right? Does that make sense? So if I took this block and scanned it, oh, and pretend this is an inch. Also, that's a pretty big inch. So if you scan, so pretend that's an inch. If I scan this area and I say 2 dots per inch, I would get 2 pixels that way and 2 pixels that way, and that's why it's exponential.
So it's more like two times.
Yes. Exactly. Yeah. So if I made it 4 dots per inch, 1, 2, 3, 4, suddenly I have 16. And so that's why as you increase the dots per inch, you exponentially increase your file size. But as you increase your dots per inch, the spatial resolution increases. More dots means more colors are available in smaller cubes, so you can pick out more things. The spatial resolution of this image is 80 meters, so that means the smallest thing that can be made out is 80 meters. So if this was an open classroom, you wouldn't be able to make out this classroom with that spatial resolution. On this has a higher spatial resolution, more dots per inch. So you can make out more features. And you could make out, probably, it's right on the edge, I'm trying to measure this in my head. You might be able to make out this classroom on a map if the resolution was 10 meters. 30, maybe still 37 feet. That's probably still smaller than that, I bet. We won't measure it, it's too late. But it's closer. Bless you. Bless you. So the spatial resolution measures the smallest item that could be discerned on your image. So the 4 things are the spectra, which wavelengths, how often, how sensitive to change, and what's the smallest feature. And obviously you actually brought up a great point, because the tendency would always be, well, let's maximize all of this. That we could, let's make it 1,000 dots per inch, and let's take an image every 5 minutes and do all these things. That would be great until you have to store all the images. So increasing each one of these to be better comes at a cost, and the cost is storage and price. If you're paying someone to do this, you're going to pay a lot more. So there's a balancing point, which is always a challenge. It's determining that balancing point where you're getting your money, you're not overpaying. You're getting enough to get what you need without overdoing it. Any questions? Good. Knowing the difference between the different resolutions is important. Some commonly used satellite image data, and I mentioned this to give you an idea. I need to look because these companies buy each other out all the time, see if any of these are out of date. But the general point is that there's a lot of vendors out there that can sell you this imagery. You can go on to their websites and purchase imagery. One of the services out there is Digital Globe, and they have a tool called Image Finder. We'll see. You can go on to any spot on Earth,
We don't have a lot of
draw a box, and see what image is available. The takeaway is that there are companies that make a living, a very good living, at selling remote sense data to universities, to the general public. The universities are consumers of this data a lot for a lot of different research projects. Private companies. I've worked with energy companies that want to build, say, an oil pipeline, and they purchase remote sense data along the proposed route to look for features. Oops, no, I don't want to submit. Oh, they're not going to tell me. Denied. We'll jump on this in a second. The point which I'm trying to show that I might not be able to is that there's a lot of imagery available. You could also have, for a higher fee, have someone record an image. You say, I would like an image of UB North Campus from tomorrow. That'd be pushing it. But say for next week, you can call up and have someone schedule time on a satellite to do a specific image research. You'll pay a little more for that. So here are, from the box I drew, here's all the different remote sense imagery available from Digital Globe. It goes back just in the last couple of years of the area where I drew the box, including as recently as last week. Let me see if I can view it. It's probably how I would expect it to look, right? Just a bunch of snow. So there's an image taken last on February 26th. Must have been cloud cover. Yeah, and it's actually that. Okay, so that shows the extent. Most of this is lake. You can see Ontario, and if I scroll down, there's Niagara County. Given that, let me go back to the one from, I said last week, it's 2 weeks ago. They're not going to let you look too, there we go. They want you to buy it. You can sort of make out, this looks like it's Niagara, oh, that's Lockport. You make that out? There's Lockport and Transit Road and the 990, there's Lake LaSalle. So you really can get this just from 10 days ago or so. And obviously it's all white for obvious reasons. So what you would do, I mean, obviously you would need to do more with this, just look at it at that resolution. You would go to Digital Globe and purchase this data. Here's another one from January 2015. I'm going to stop after this because this would be addicting for me. We'll spend the rest of the time looking. Oh, yeah, here's Buffalo again.
That's
Grand Island, yeah, there's back in January 13th, a partially frozen lake. This is a long lost memory, but if you remember, December was nice. We were above normal temperature and very little snow. Then January hit. So the lake wasn't that frozen. So this is just from one vendor. Okay, one more. They have a lot. Here's also February 16th, 2015. Yeah, I think a lot of them are done that for that reason. They're surveying the lake ice. And so the companies make out well with this, you know. Someone, maybe the weather, NOAA paid them to take these imagery so they can double dip. Someone paid them to take that image of the satellite. Now I come and say, I want that image too, and they're getting money for it again.
But if it's NOAA, you can get
What? If it's
NOAA paid for it, you can get it.
That's true. If it would be public domain data. So just to show where you can get a lot of different imagery. And this is one of those things that just in the past year has become a guided student, Deb Naylor. I think she's teaches some class now. She's awesome. Was doing a project in Uganda. And it was amazing to me, being a little older, how much data was fairly readily available, where you'd be at a loss a couple of years ago. So there's the point, there's a lot of raw data available. I know one thing I will not do is like name companies. I'm not going to ask a question like that. Just the takeaway is there's a lot of sources available for remotely sensed data, and as the screenshot showed, even to the point where we saw data from just 14 days ago already available. Some militaries can do it a lot sooner. I was told you would. I don't want to know. I mean, I think they can do a lot more things than any of us here, including me, can imagine. When this is good, well, I can't believe how long. In 2001, everyone remembers the World Trade Center, but there was also those couple other things at the anthrax mailings, and there was a sniper in Washington D.C. that was randomly shooting, killing people. I heard that they had after an incident, they had remote sense data of very high spatial resolution, and within minutes after another shooting was reported, and that helped catch the two. It was two suspects, the father and son, that they eventually apprehended. Was it about 40?
It's about 45 minutes per colonist or theater.
Was it about that? That's about what I had heard. Yeah. So like within an hour, FBI and all the agencies on the case had remotely sensed image of an area where a sniper attack had occurred.
Not DoD, it's NRO. Yeah, NRO.
I think so. Yeah, it's above. The people in the DoD don't even have access to a lot
It's
of.
a National Reconnaissance Agency.
Okay. Yeah.
Yes. All they do is sit there and watch satellite feeds.
Yep. And it's kind of scary, but on the other hand, it helped catch these guys. There's always a balance. That's even before all the NSA revelations that came out about a year ago. Wave to them. So remote, that would be good temporal resolution, wouldn't it? Having access to that data very quickly in a time of crisis like that, where they're trying to apprehend somebody. Common uses, satellite image data. We've talked about this already, but meteorological satellites are a big one, as someone noted. A source of all that imagery I just brought up is probably for monitoring lake ice. That's why there's so many images available just over the last couple of weeks. Lake ice has been a big deal this year because of the record amount of ice on the Great Lakes this winter. I think we did break the record. Sea surface temperature, they're monitoring more and more because that really affects the global climate. I'm sure our crazy winter in the northeast U.S. ties back to an anomaly in sea temperature somewhere. El Nino would have the opposite effect of warming of the Pacific Ocean. I thought we were going to have an El Nino winter. I was hoping for that because it's usually nice here. That wasn't meant to be. Any questions? So there's a lot of different applications of remote sense data, satellite data, and the ability to get it quickly. If there's no questions, we'll switch gears to talking about elevation. Let's still talk about raster, although some of the things we'll talk about will not be raster in a moment. We're going to cover some different ways in which we model elevation of the Earth's surface is our next topic. Digital elevation modeling is a technique involving measuring elevation of the land surface. It's a fancy definition of a DEM. Basically, a DEM is a raster that represents elevations on the surface of the Earth. Well, actually, when I refer to digital elevation model here, I'm being more generic than that. And on this slide, I have some different basic implementations of how do we map elevation. And there's different ways in which we do that. We'll talk about 4 tonight and then be done. Most commonly, you'll use the first 2. the digital elevation model, or a DEM grid, elevation contours, but we'll also talk about a profile or a TIN, a triangular irregular network. Those are the 4 topics that we will cover for the rest of tonight. I don't have a viewer for it. Oh well, I'll come back to that. The first type of elevation modeling that we'll talk about is raster, or a grid. As we saw, and luckily just about everyone got that right, a raster is a grid of like cells. And just to review that quickly, a raster has one cell value assigned to each pixel. Everyone got that right, or almost everyone. In a DEM, the value is the elevation in that cell, an average elevation. So that's a DEM is a specific implementation of a raster. You'll see it is a DEM generically. Now in the United States, the data set is referred to as an NED, or National Elevation Data Set. You can download these for a wide part of the U.S., and there's a website, ned.usgs.gov, National Elevation Data Set. And they have this raster available. We'll talk about the different sizes available, I think, next week for most of the country. Actually, it looks like all of the 48 states now have some level of resolution available. They're just working on Alaska. Again, that's specific to this country. So, a review slide. If you remember, here's another look at a raster to refresh your memory there. This is from one of the February lectures. And so is this. You might remember this. I think it was February 7th. So each cell, there's a cell in the raster, and but with a DEM, the number, as I said, represents an elevation. So this is the averaged elevation over that cell. And obviously it's averaged, if this is a 30 meter by 30 meter cell, the elevation may vary, but this is an average over that area. And what we can do is you can use a DEM to model flow. If excess water occurs here, we can look at this and you can model using something called spatial analyst. I'm pretty sure that's one of the labs will cover that near the end. But you can model that the excess water will flow this way. It will not flow that way because it's higher. So DEM's elevation data sets in conjunction with specific software like spatial analysts are very good for modeling hydrologic data, finding watersheds. Where will water flow? Where will floodwater go? Where will pollution go? If pollution occurs here, you know that it's fairly contained. The pollution isn't going to climb up the hill. If a lot of pollution, if an oil spill occurs here, you have a problem because if that's the high point, it's going to disseminate. So digital elevation model raster grids are very useful for modeling hydrologic flow of water and but other things like pollutants and so on. Questions? You can, here's just some screenshots from ArcGIS showing some of the tools available. This is US based, but I'm pretty sure you get these files in other countries. From the US government, you can download a file called a .dem file. that contains these elevation grids. Using this ArcGIS tool, you can convert that to a ESRI raster grid for use in ArcGIS Desktop in the spatial extension. This is a DEM raster that I put together to show the class of Niagara County, New York. Can I have that on the next slide? So you just, instead of, remember this is a raster, so we have a range of colors representing the elevation values in each. And if you, is anyone from Niagara County? No, then you don't know what I'm talking about. But in the, this is Lockport. North of Lockport, it gets very low, and like north of Niagara Falls, it's the same feature. This is called the escarpment, and the escarpment is what Niagara Falls falls over. North of Niagara Falls, the land gets flat and low, so that's what we see here. Then we see the Erie Canal there. But again, it's a raster. What you see is a raster data set, and just to prove that, I zoomed in for the next slide to show you how it's a grid of pixels like we talked about. And so I identified a pixel here, and as we talked about, I showed you a couple slides ago, every pixel has one value. In this case, the value 136.5 indicates the elevation above sea level. So here's a real-world depiction of a DEM raster from just north of here, near Lockport. So everyone got a sense of a raster? A DEM raster. A DEM is a raster implementation of elevation. It's very easy to process. There are many programs for processing these and many applications. I mentioned one already, Spatial Analyst. Disadvantages, and we mentioned this disadvantage in terms of rasters earlier, fixed resolution, where you waste a lot of space. If this area is all one, it's perfectly flat, you're wasting a lot of space, with the same pixel value repeating over and over. So there's a disadvantage. But in general, rasters, as far as elevation, hydrologic modelers, rasters work very well. Any questions? And this would be something like in the environmental modeling geography course, something that would you would use a lot in a course like that, environmental modeling. And another, it's not an elevation, but another example, got too many things open. Just another example of a DEM, not a DEM, of a raster that I've downloaded here is this raster of land cover. The legend. Yes, we don't. So in a land cover raster, each of these colors represents a type of land cover for that area. And I don't remember all of them, but in general, the red shades are developed land, which will make sense as you zoom out. The green shades are forest. They use blue for water, and brown and yellow represent agriculture. So it's an example of a raster, and then the blue can also represent wetland. You get a good general sense of the Buffalo area from this land cover. You see all the developed areas, a lot of agriculture to our north. There was a whole series before Western settlement. There was a whole series of swamps running just up below the escarpment from Niagara Falls towards Rochester. Most of that has been. That's why Amherst has such a problem with houses sinking. This whole area, where you are right now, was a massive swamp 100 years ago. So some people in Amherst, not too far from the campus, have had trouble with their houses sinking, which is a problem. And it's because of the geologic history of where we are right now, as we speak. Okay.
How's this thinking?
Yeah. I didn't think what I said was that striking. I can't think of anything more clever to say, so I won't. I was teaching once at DOT in Syracuse, and it was quietly. There was someone who was having an argument in the other office, and just started letting out all these profanities and swearing so loud that I broke class. So you might as well take a break. And no one can. I've seen worse. So these are all rasters. When you teach in the jail, that hasn't happened. I wonder if there's no people living right above the jail anymore. We used to have all sorts of interesting things go on because there's bedrooms and common areas right above the jail land. I haven't noticed that in a couple of years, so I wonder, they've kind of redone Wilkeson, which is a good thing. So that's rasters. Another way of implementing elevation mapping is contours, which is vector-based. So now contour elevation mapping is a vector-based data set, not a raster-based data set. Because digital elevation models are so widely used for elevation mapping, sometimes people can think of elevation mapping as always raster, and that's not the case. Contours are a vector line type vector feature class that represent an iso line. In other words, where are areas of like elevation. So with the vector lines, if I were to walk along that line, I would know that I'm not going up or down. Walking along this line would be completely flat. I know that if I walk from there to there, I'm walking downhill for a distance of 200 feet. So each of these lines, and I'll bring up an example map from Esri in a minute. Everywhere along this line is 6,200 feet above sea level. Everywhere along that line is 6,000 feet above sea level. And maybe this slide helps show that a little better. I put a raster diagram behind the iso lines to show how they're related. I like the USGS version better. Let's read. That's what I want. This is a USGS topographic map. We'll talk about this series of maps, I think, after break. The very first. So even as we look at this map of UB, we can see contour lines. So along the Willis Park Highway, this is 585 feet above sea level, that line there. There's 590 feet above sea level, 595, and so on. So we can, through this, even though it's not a raster, determine that if you're driving this way on Millers Park Highway, you're driving uphill. This isn't the best example because there's not a lot of elevation change where campus is. But if we were to go to yeah. There'd be a little bit of elevation change here on the falls. I mean, it's not a good example. It's so. I don't like that example. And if you think about this, there's the Niagara escarpment that I was talking about that I showed you the DEM of. As you might visualize, vector lines spaced far apart mean a relatively flat surface. When you see a lot of lines together, you know it's very steep, because suddenly, instead of taking 1,000 feet to go 20 feet up or down, you're going 20 feet up or down just in a couple feet. So these are contour vector lines. If you think about it, this should make sense, but I'll point out they can't cross. You can't cross the paths. So if think about that, if you don't believe me. So that line, everywhere along that line is 100 feet. Let's say if I tried to draw one 120. You see why they can't touch? Because now somehow that's 120 and 100. That's not possible. So contour lines can never cross. And if you look at the map, unless there's a mistake on there somewhere, you'll notice they never cross each other. As they come closer, you know the elevation change is steeper, but they don't ever cross. Any questions? Those two I'm all over the place now. So what you will use DEMs and contours most often for elevation modeling. You'll see both widely used and used. Question?
Is there gonna be like if you can't find somewhere like even level at the same elevation, it's gonna be so large the contour line?
So there is.
The area using the line will be so large. If you can't find the exact elevation.
I think what you're getting at, you can't use that to find an exact elevation. Is that what if that's what you're saying, and you're correct if that's what you're saying.
I'm saying if somehow you could get an area missing that contour line is so large.
You could. So for example, if it's flat, you could have a large area in between. Say it's completely flat. Within here would be flat. Within the interval, contour lines have what are called an interval. And on this map it's 200. There's 200 feet between every line. So one other thing that relates to what you say, I think, is you can't get the exact elevation. If the interval is 10, so you have 60 here, and 60 here, and then two 50s, there could be a wide area in here if it's flat. But I don't know, if it's within the interval, I don't know what changes. This could go to 59.5, right there. And I would never know it because it would never hit 60. Does that help kind of? So it isn't perfect. You would need to use a smaller interval. Sometimes on a map, you might see a benchmark to indicate this particular height somewhere. And I bet we could find those on the map here.
So if it's a higher interval, it's less accurate?
Yes, that's absolutely the case. The higher interval will be less accurate. Because here, variation within 10 feet, you'd lose. If it was 100 feet, anything within 100 feet would be lost. So you're absolutely correct. You might see a little circle, say this went to 60.5, you might see a circle here. And something like this would be a mountain or a hill. And wherever possible, you'll see this a lot, they will indicate. Look, like here, it indicates a spot elevation, probably the airport, there's a 602. They've indicated a spot elevation to help augment the contour data on the topo maps. We don't have, maybe if I go to southern tier, you will see, I can't find one. There we go. You'll see peaks called out to help with that problem. Like here, the near Allegheny State Forest, I think they indicate a peak here, 2171. A peak is indicated here at 2245. Without that, without the 2245, we would only know that there's a 2240. The interval looks like it's 20 on this. So we would know that it gets to at least 2240. It doesn't get to 2260. We would know within 20. Going to your comment that the smaller the interval, the more accurate. But in cases like that, they put the exact number on the topo map at least to indicate a peak.
So if the lines are closer together, does that mean that it's a more rapid change in elevation?
Yes.
And that, or could it just be a smaller interval?
It should be. That's another good question. The interval on the map should be the same in most cases, regardless.
Okay, so it's just relative.
It's just relative,
Okay.
yeah.
Okay.
So to answer the question, lines close together mean that it's steep. I can't think. Every map I can think of, the interval is the same on that map. A different map might have a different interval. Like if right now they're 20 feet. I bet if I zoom out, it goes to a different interval. But that has a different interval, which is possible to read on the projector, but it would be consistent anywhere on here.
So is the raster more accurate because it's doing the blocks with like every individual in the elevation change?
That's a good question. You could argue it depends. Either could be more accurate. I might actually indicate think the vector is more accurate because it's showing every little deviation, and you're not stuck to using blocks.
Okay.
But that depends on the size of the blocks and the interval.
So it depends very much on the size of the scale.
Exactly.
Okay.
Yeah, exactly. So any questions on the intervals? So interval, lines can't cross, vector based. I think I hit the key points on the contours. Another type of modeling that frankly I don't use as often is very different from the raster and vector models we just looked at, and that this is a side view. A profile elevation modeling is usually used in conjunction with other models. You use a DEM raster or contours to create it. A profile is looking from the side. So here, if I'm drawing, if I walk from here to here to here, I'm walking down. And it actually shows the profile from the side instead of looking from the top down. Does that make sense? So a profile is a side view of elevation change. I found this, this would be cool, Laurel Highlands, Pennsylvania. It's like a neat place to hike near Johnstown. I found this in the trail brochure. This is a side view of the trail. It's a long trail, 44-mile hike. I don't think I'm in shape for that. But this profile view gives an indication to the hiker what's in store. The profile view shows that there's going to be rises here, and then you're going to drop down to the stream here, and so on. So this is an example, and recreationally, this is an example of a profile view. And I found this cool, where is it? I found a cool tool that also indicates profile views. It's on the website heywhatsthat.com, where you can draw a line and get a profile. So I'll choose Niagara Falls. Where exactly is the fall? There it is. If I draw a line from a Falls View Casino to Seneca Casino, I'm not a gambler, but just I'm not drawing it. There we go. So there's a side view profile of my line that I drew across casino to casino. And I think this is a good example if everyone can visualize Niagara Falls. Notice how we can visualize the gorge. So if we walk this, you walk down the gorge, walk along the bottom of the river below the falls, and back up on the west side. So hopefully this also helps illustrate for you a profile view. And you could do this just about anywhere. Certain?
The profile is cut.
It's cut off.
Looks like it's cut for a contour map because you got nice steps.
Yeah, I bet it is using contours. It's a good using contours and not DEMs. In this case, maybe the raster would be more accurate. Going back to that question. So, like in the in less extreme example, for us to walk from here to the waterfront, oh, it's still showing the original points. So though there's the rest of this is a profile walking from UB to the Buffalo waterfront. So you can see the examples of profile views. Or that's kind of cool, driving from here to the Pacific Ocean. You can see the lane slowly ascending across the Great Plains. You see crossing the Rocky Mountains, Great Basin, and some of the coastal mountain ranges, and then finally down to the Pacific Ocean. Yeah, that ties back to that shape, area, distance, direction, the curved line because of the projection. See, it all comes together. So that's a cool tool. I hope that also helps illustrate what a profile view is. Most all my work has been with contours or DEMs, but we've had to build profile views. We'll talk about this with analyses. We haven't done as much of this since the wind credits dried up a little bit, but people that want to build a wind farm, that's something that's changed since I'm young. If you drive across the country, there's windmills everywhere now. That never used to be. But when you put in a wind farm, you have to indicate where it's visible and where it's not. So you can use these profile views to help indicate, to build a view shed. Where can I see my windmill? You don't want people traveling from all over the world to Grand Canyon for the beautiful view and have like 100 wind farms right behind it. All right.
The city of Portland has an ordinance that no building can be so tall that it obscures
Portland,
the
Maine.
mountains.
Yep. It's like 3 stories tallest building.
No, it's Portland, Oregon.
Oh, Oregon. I think Maine has something like that too.
But yeah, every time you build a skyscraper, you have to do a profile to show that you're not obscuring the mountains.
Exactly, Mount Hood in the Cascades. So another profile view. I also, the Erie County Water Authority wanted to put up radio towers so that they can radio their crews and have the line of sight is important. But where can we put a radio tower in Erie County that has the most coverage? So the Erie County Water Authority truck could be anywhere within Erie County and be picked up. So we use profile views to help find a tower. We'll talk more about that with view sheds in a couple lectures. So those are a few cases where profile views can come in handy. Almost done. Another type of elevation modeling is a TIN, or a triangular irregular network. It's a vector-based elevation data model, but it's a little different than the vectors we talked about. A TIN is an interconnected network of triangular faces of equal aspect. It's vector-based. Each vertex has an x, y, or z value. It's originally derived from the rasters, and the raster slopes helped produce these points, which then produce these triangles. So in this example, that triangle is flat, and it has a value indicating the aspect. And we'll talk about the aspect is where it's leaning. So if the aspect is 0, if the triangle is straight up this way. So when I say the triangle is flat, I don't mean it's flat this way. It could be leaning in a certain direction. But anywhere within the triangle is flat. So aspect is how is it leaning? Is it leaning south? Is it leaning north? And so on. That's what's called aspect. And in a TIN, or triangular network, each of these triangles has a similar aspect. I think the next slide shows that a little bit too. So here is converting point elevation points into a TIN. We talked about the point cloud last week in terms of LiDAR. where the LiDAR satellite just blankets the Earth and returns, tens of millions of elevation points. That could be converted into a tin here. So you can see these triangles of an equal aspect. So here's another view of a tin showing its x, y, and z value at the point elevation points. If I asked about a tin, I would ask a generic question, what is a tin, not for some of the specifics like that. So here's an example of representing slope in a digital elevation model, the first thing that we learned. And here's a view of a tin. Oh. And that's it. It's 9 o'clock, so I think that's a good time to wrap up. We'll continue talking about elevation in 2 weeks. And